So we're going to play more chain rule game today. So we're going to start by looking at this well-known formula. If you did not know that the formula for the volume of the sphere was 4/3 pi r cubed, you do now know that the formula for the volume of the sphere is 4/3 pi r cubed. If you do know this, it's because we place undue value on knowing kind of like random niche facts, like areas 1/2 base times height or pi r squared or things like that. The advanced version of this is that volume is length, width, and height. That's all there is for volume. And if it starts being curvy, then you do integration. But that's not as useful to our purposes right here. We want to look at the volume of the sphere. V is 4/3 pi r cubed. So let's find the derivative of this function. Just using what we know about derivatives. What is the derivative of this function? If I just said find the derivative. Find the derivative. If I just said find the derivative, we would probably write v prime. And what is v prime? Four-thirds pi is constant. We want to take the derivative of r to the third, and that's going to be 3r squared. Just using our nx to the n minus 1, our favorite derivative rule. Then we would want to simplify this. If I take 4/3 and multiply by 3, I will have 4. So 4 pi r squared. That is the mechanics of what's going on here. This doesn't really help us interpret what's going on. This is just mechanics that you've been programmed. You've been learning about. I totally didn't program you. I'm totally not trying to Jedi mind trick you into convincing you that I didn't just indoctrinate you earlier this semester with nx to the n minus 1. So this is just expressing our programming of nx to the n minus 1, find the derivative. This doesn't really answer the question, what does the derivative mean? Because we wrote v prime, v is a function of r. This is how velocity is changing with respect to r. That's what we want to write. So when we say find the derivative, we need to be specific about what derivative this is. That's what we want to get at today. So specifically, what we wrote here, in this case, v prime I want to write this derivative in Leibniz notation. What did we take the derivative of? What did we take the derivative with respect to? So the numerator is what we took the derivative of. What do we take the derivative of? It's v. What do we take the derivative with respect to? That's r. So this derivative is dv dr. This is the rate of change of the volume with respect to the radius. The derivative is a very generic term. Rate of change is a very generic term when we're talking about specific things that aren't just generic functions, f of x equals x squared minus 3x minus 4, something like that. Here, volume is 4/3 times pi times the cube of the radius. So when we say the derivative and apply our mechanics, we're looking at dv dr, how the volume is changing with respect to the radius. If the radius increases by 1, then the volume will increase by approximately 4 pi times the radius squared. Any questions? This makes sense. The volume is proportional to the radius. The volume is proportional to the square of the radius. The radius is 1 of the centimeters, and the radius squared will be 2 of the centimeters. So multiply those, we get 3 centimeters. We want to imagine a different scenario. Suppose that we have a sphere, and the sphere is a balloon that we are blowing up, and we are and we're looking at how the balloon is expanding over time. Suppose that we're interested in how the volume is changing with respect to time. Suppose are there 2 L's in balloon? Let it go. How do you spell balloon? Okay, you don't have to spell it. There are 2 L's in balloon. This is one of those words that looks wrong no matter how it's spelled. When it's spelled correctly, I'm like, oh, that looks wrong. When it's spelled with 1 L, I'm like, oh, that looks wrong. It's like this word never looks right. There are some words that when you write them, in my mind, they never look like they're spelled right. Anyway. Suppose we're blowing up a spherical balloon, and we want to look at how the volume is changing over time. I'm going to say over time because we usually say that way. Let's suppose that we're blowing up a spherical balloon. The volume is changing. We're putting air into the balloon, and the balloon starts expanding. What we want to be able to do is look at this expression, how the volume changes over time. And here is a question about how the volume is changing with respect to time. What is the derivative of the volume with respect to time? That is the connection we want to make when we're in calculus class. We want to start thinking of how things are changing. And we want to measure we want to think about how we are measuring those rates of change. So the volume is changing with respect to time. When we think about this in terms of derivatives, we want to think about the numerator is what's changing, and the denominator is how we're measuring that change, over what we are measuring that change. Here, we are changing the volume with respect to time. So the rates that we had in dV/dr, when we just took the derivative, the rates of dV/dr are cubic centimeter. Let's just use cubic centimeters. Would be cubic centimeters per centimeter. So the units here would be but the units when we're changing the volume with respect to time would be units of volume divided by units of time, maybe seconds. That seems reasonable for blowing up a balloon. If it's a gigantic balloon, maybe we'll have it in minutes. If it's an extraordinarily gigantic balloon, maybe it will take hours. All of them would be valid, but some of them would be weird. You could blow up a balloon and say, what is the rate of change of volume? And measure it in cubic meters per hour, even though a balloon is not going to really, it's not reasonable to measure a balloon in cubic meters because they're small, right? But you could do it. It's like when people say things like, oh, it took a fraction of a second. An hour is a fraction of a second. I mean, that's not what we mean. But like technically an hour is a fraction of a second. But when someone says a fraction of a second, you know what they mean. And you're kind of being a dick if you interpret it otherwise. Do you know what I mean? It's like, it's the same, can I go to the bathroom question. Student says, can I go to the bathroom? The answer is just fucking yes. But they're like, I don't know, can you? What a prick. If you're that teacher, fucking knock that off. Go ahead and comment down below if you're that teacher. Joke's on you, I fucking turned comments off. You know what I mean? By the way, if you're that pedantic and you're not doing math, you're being a racist. Side note. So what are we talking about? Oh yeah. So this V prime, this dV, this is the rate of change of the volume with respect to the radius. Weird units, centimeters squared, or cubic centimeters per centimeter. For each centimeter increase in radius, we get a certain number of, we get 4 pi r squared cubic centimeters in volume. So now we've changed what our denominator is. We're looking at dV dt. Now we look at this equation, we say, well, there is no t here. This is a volume with respect to the radius. So as we're blowing up the balloon, not only is the volume changing with respect to time, this will cause the radius to change with respect to time as well. So note that in this scenario, the radius is also going to be changing with respect to time. Say over time. The radius of the balloon will also be changing over time. Radius can be measured in like centimeters, and we should use the same time for both of them. So we're going to have this other derivative, dr dt, We'll probably have units, the units of R will be centimeters. And the units of time are gonna still be in seconds, because we should match those up. So as the volume of the balloon is increasing, the radius of the balloon will also be increasing or decreasing if we're deflating the balloon. So this is what we're referring to when we're referring to related rates. So dV/dt and dR/dt are related rates. Role play. They're related because the volume and the radius are related. Here's a relationship between the volume and the radius. So their rates will be related. Earlier, we had taken the derivative of 4/3 pi r cubed. And that was, we got 4 pi r squared. That was the derivative of volume with respect to the radius. But if we wanted to find the derivative of volume with respect to time, instead of just writing dv dr or v prime, if we wanted to know how the volume was changing with respect to time, we would need to use the chain rule. So the derivative of volume with respect to time is the derivative of volume with respect to the radius multiplied by how the radius is changing with respect to time. If we wrote down the units for each of these, dV, dr, V is measured in cubic centimeters, R is measured in centimeters, dr, dt is going to be measured in centimeters per second. So when the seconds cancel out, we're left with cubic centimeters per second. So the units tell us that things are working out. Questions? So the idea here is that we think about the rate that we, one of the rates that we want, in this case, how the volume of the balloon is changing over time. We think about what we know about that function. Volume is 4/3 pi r cubed. We find the derivative, but we have to identify the derivative of 4/3 pi r cubed. When we write 4 pi r squared, that's the derivative of v with respect to r. So the chain rule says multiply by the derivative of r with respect to time. Then we can make sure everything works out by doing a unit analysis like we always do. Any questions? Comments? Slide remarks? I didn't leave enough space. Let's suppose that dVdr is 8 centimeters per second. The idea here is that we are putting air into the balloon at a constant rate. We have a machine that can reliably push 8 cubic centimeters. I don't even know if this is a lot. That's why I'm glad that this class takes place before physics. Because then you take a physics class and you find out all the numbers that I use in my examples were just like bullshit made up numbers. It's like, well, that doesn't make any sense at all. Then it's a real problem when you get to Calc 3 and I still don't use like realistic numbers. And I'm like, oh, what is the total charge on this plate? And you're like, oh, 88C, that seems like, no, that doesn't seem right at all. But then you remember that the plate is like also 100 square meters. And it's like, oh, Leach, where are you getting these units? I'm like, oh, I don't know, I'm just making shit up. I only care about the math part. I'm not trying to be an engineer up in here. Do you know what I mean? I don't have Calc 2 next semester. So if you're taking Calc 2 next semester and you're going to have like tanks that are built in the shape of a cone. All of you engineers are just going to have to put that shit aside. The tank is the shape of a cone. You don't get to ask like, oh, why would you build a pool in the shape of a cone? That seems really inefficient and bad and difficult too. No one would do that. That's not the point, right? So just all of you, because I know a lot of you are going to be like all engineers and shit, and you're like, oh, that doesn't make any sense at all. You should like make it like roundish on the sides, but not pointy at the bottom. That is a bad design. That's going to break. When you encounter that, I want you to, because you're going to encounter this in physics as well. You're going to do things like, this is what happens when we ignore friction. And you're going to be like, oh, what about friction? That comes later. That's just it. We're trying to make the problem simpler. Do you want the easy problem now so that you can build up to the big problem? Or do you want the big problem now and so you don't know what's going on? That's what you want to remember. Oh, this is going to get more interesting in the future, right? The only time you have to worry about air resistance if you're throwing things too fast. If we're just like throwing things back and forth, if I'm just like throwing pens at students and stuff like that, we can safely ignore air resistance because I'm not throwing the pens very hard, right? It's only an issue if I'm really flinging the pens at the students, right? But this is a college class, so I'm not going to throw the pens very hard. Now, back in high school, air resistance was important because I was trying to get, high school students' attention. You got to wing those pens at the students. Boom. But my arm's all out of shape now. That's actually why I had to stop teaching high school. Well, you're losing a couple miles per hour on your fast pen, Leach. Well, yeah. I'm building a little more curve into it, though. Useful for getting students to think they can safely sit in the back. I'm like, I'm like, oh, damn. Wakes up the student. You know what I'm talking about? There's a private school. You're totally allowed to do this shit. I'm just kidding. Don't at me in the comments. Because you can't. So we're filling a balloon with a constant rate. I like to do it this way because I can imagine a machine that can put out a lot of pressure so that the balloon is not significantly pushing back on the machine, right? Like at a certain point, if like blowing it up, just like with our lungs, at a certain point, the balloon's like, oh, no, I think I could take this guy. And you're like, oh, blowing, and the balloon there's more pressure pushing back. The balloon is going to put more pressure on your lungs. Hopefully not to the point where the balloon's like, oh, nah, fuck you, and like fills your lungs up suddenly. But it starts becoming more difficult. But we've got a machine, we're hooking that up, and the balloon is no match for our machine. So we can maintain a nice constant 8 cubic centimeters per second, which as previously stated, I don't even know if that's a lot. All right. How fast? I'm just going to write down the typical related rates problem. How fast is the radius increasing? How fast is the radius increasing at 3 centimeters, when the radius is 3 centimeters, 6 centimeters, 12 centimeters? So we're going to look at, we have the velocity, change in the volume. I spelled T wrong. None of you stopped me. That's minus 20 points for everybody. I'm just kidding. It's minus 1,000 points for everybody. So my question is, what's happening to the radius at these different sizes of balloon if the volume is going to be increasing at a constant rate? So when I say how fast is the radius increasing, this question here we need to be able to translate this into calculus. We're saying what is dr dt? And we want to do this not at different times, because even though we're measuring over time, time is not one of our variables. Because what we're writing, we're going to start by writing v equals 4/3 pi r cubed. So I want this at different radiuses. So here r is 3, r is 6, and r is 12. So we write 4 pi r squared. That's dv dr. This has to get multiplied by dr dt, presumably the thing that we're looking for. Or presumably one of these things is what we're looking for. That sentence was different when I thought about it at first. So here is how we get at the relationship between the two rates, how dv dt is related to dr dt. They're related by multiplication by dv dr. The dv dt, that's our constant rate of 8 centimeters per second. Four pi and the r squared. Do this the other way around. So the dv dt is something that we know, 4 pi r squared. That's where we're going to be putting our different values for the radius. And dr dt is what we're looking for. So dr dt I'm going to divide by any factors that aren't what we're looking for. So I'm going to take dv dt and divide by 4 pi r squared. So here we see that when the radius increases, dr dt is going to be lower. You see that dr dt is inversely proportional to the square of the radius. So let's calculate dr dt for various values of r like we have here. So dr dt evaluated at 3. So 8 divided by 4 is going to be 2. So we'll have 2 over 9 pi. Centimeters per second. So we notice that the things that we're plugging in, we're seeing that how we're looking at how the rate changes for different values of the radius. This makes sense because when the balloon is bigger, adding 1 centimeter of radius adds a lot more when the balloon is large, because there's that 1 centimeter is spread out over a giant volume. So if the volume is changing at a constant rate, then adding a fixed amount of volume is going to require less change in radius. Notice that when we went from a radius of 3 to a radius of 6, when the radius doubled, the volume was divided by 4. This is why I didn't cancel the 2. So we can see 2 over 9 pi. If we divide that by 4, we have 2 over 36 pi. And that was expressed up here. dr dt is inversely proportional to the square of r. dr dt is some constant divided by r squared, inversely proportional to the square. That means they're going to be going in opposite directions, and that and it's the square. So when the radius is doubled, dr dt is divided by 4. So that means if r is multiplied by 2, if r is multiplied by 4, dr dt would be divided by 16. color coded, so then I couldn't stop. So here we double the radius again, and here we divide divide dRdt by 4. Questions? Does everybody think? So an important thing to note about this particular problem is it is not about blowing up balloons or how spheres are changing with respect to their radius or with respect to time. The idea is understanding what we mean when we talk about derivatives. When we just say the derivative, that's a very generic term. That's very nx to the n-1, gives very mechanical vibes. But we need to think about when we find the derivative with respect to a variable, think about what those things mean. And it's the same thing that we meant when we talked about slope. dRdt is how the radius is changing with respect to time. The units of r are centimeters, the units of t are seconds, so we get centimeters per second. It's the same thing we were doing way back in elementary algebra when we first started studying linear equations. It's what the slope meant. DVD bonus material. I got to talk about inverse proportions. And then we just, so this related rates thing, this is just the framework that we get to talk about the chain rule. Any questions? Sometimes in math class, the story, the important part of the story is not what's written on the outside, not what's written on the tin. I don't know if anybody's seen the movie Chef. Has anybody seen the movie Chef with Jon Favreau? That movie is not about a chef. I mean, it's about a chef. It's not about cooking food. It's much more interesting if you think about what Jon Favreau was doing and why he did that movie. I actually recommend learning that before you go watch the movie, because it makes the movie that much better. You know what I mean? That's your homework for the weekend. Watch the movie Chef. All right. Ain't no one got time for that. We've got to do related rates. That's going to do it for today. I will see you all on tomorrow. Hopefully tomorrow I will try to be more coherent. If not, I'll just give you all the problem to do. That's it for today. I'll see you all on tomorrow. Everybody have a good day. Thanks for playing.